Hello, everybody, and welcome back to another episode of V Next. I am your host, Mike Walker, and today we are going to demystify quantum computing. Yes, that's right, that often elusive, far out distant technology that we all like to talk about and hypothesize around. However, we're starting to become closer and closer to this really becoming a reality. And as that happens, and we start to get better visibility into the sorts of applications that will be required, it's even more important to demystify this particular space. So today, I'm really happy to have Delbert Murphy, who is a worldwide community lead for quantum computing at Microsoft. And so, if there's anybody out there that has seen all the different perspectives around this, it's definitely Delbert. And we're going to dive into what is quantum computing, what are the practical applications, and probably most importantly, what aren't the right applications for this technology. So, without further ado, let's jump into it. Delbert, welcome to the podcast.
Thanks for having me, Mike.
So, I'm really excited about having you on today because we're talking about one of those topics that people like to kind of fantasize about. It's one of those technologies that's just far enough away that I can kind of touch it and feel it, sort of, kind of. And so today, demystifying essentially quantum computing. And I couldn't imagine a better guest. You run the worldwide community for quantum computing. And so, Delbert, welcome. And maybe could you give us a little bit of background about you and your journey to get to this point?
Sure. And I think one thing to keep in mind is that this quantum train is thundering down the track at us. So it's definitely uh, change is coming quickly, and there are things you can do right now. So it's not just out in the future. So I'll just touch on that very quickly. And then my journey with quantum computing and quantum mechanics started a very long time ago, and I would say I had I got a math degree in college, and then just because I loved math and I already knew how to program computers, so I knew no matter what, I had a job. You know, before I even went off to college, I worked as a professional computer programmer. So and those languages and formalisms like that come very easily to me. So I knew I had a job. I could major in math and really enjoy learning all of that stuff. Shortly after graduation, I had a friend loan me a book called The Dancing Wu Li Masters. It's by Gary Zukav, and it was about Eastern philosophy and quantum mechanics, and how they tie together, and especially one of the new developments um, that was really coming into prominence around the time that Gary Zukav wrote that book was Bell's theorem. And it's pretty technical, but it's essentially proof that the quantum world and the world that we perceive are just not quite what we think they are. And so um, the linkages between Bell's theorem and Eastern philosophy was just a really neat connection. And since I like Eastern philosophy anyway, it was really cool. And so that started this journey for me, um, studying quantum mechanics. And then fast forward to December of 2017. So that was, not too terribly long ago. I was in a Microsoft internal conference called MLADS, which is the Microsoft Machine Learning and Data Science conference. There are literally thousands of folks from around Microsoft who, at least at that time, got together in person at the Microsoft Conference Center and exchanged ideas about machine learning and data science. And because that's so important inside of Microsoft, that conference, draws a lot of intellectual firepower. So it's great to just go and to learn, and perhaps present now and again. And at that conference, Todd Hamdahl, the then CVP of Microsoft Quantum, presented a recruiting. It was basically a recruiting pitch in a keynote for folks to download and try the Microsoft Quantum Development Kit and Q Sharp language. So that worked inside Visual Studio, and they were going to release it about a week later, about a week after this conference. And so he wanted to enroll a bunch of beta testers, and he was recruiting, for positions within the quantum team. So it was it was really a fantastic event. And so after the keynote, I walked out of the auditorium, and in the Microsoft Conference Center, there's that chunk of cement that came from the Berlin Wall.
Yep.
Remember? Yeah. And so I sat on that chunk of cement, went and plugged my laptop into the power cord into the outlet over there, and I sat there for the rest of the conference and coded in Q Sharp. I
Nice.
completely ignored the rest of it. And it's neat because I've been around Microsoft, for 15, 16, 17 years, something like that. And so old friends would drift by, at breaks and say, "Hey, how you doing?" You talk a little bit, and then they go off to their thing, and I'd go back to Q Sharp. And so that's when I really made this connection between computer programming that I'd been doing, literally since 1969. I started programming analog computers with my dad at the Highway Safety Research Institute at the University of Michigan. So anyway, this merging of computer programs and quantum mechanics and all of the interesting, kind of, as Einstein called it, spooky action at a distance. All of these things that quantum mechanics experiments turn out now, it's really been fascinating. And it turns out that there are certain classes of problems that this is just a terrific solution for. So that's kind of how I got to where I am today.
And it sounds
And
like, and I'm finding this with a lot of people, Delbert, is uh, the folks that are involved in this. It's really about being their passion, and they don't have formal degrees in quantum mechanics or what have you. But now that quantum computing has become so approachable, and when you went to that conference and they were like, "Hey, you can download this SDK and you can code in an IDE that you know and love." Great. Now it's accessible. And so if I'm understanding you correctly, it sounds like it was kind of the meeting and the merging of a passion with something being actionable and available that you can embrace right now. Am I getting that right?
yeah, exactly. And there's just one little thing I skipped over, um, and that is we have to be careful. It's just like some of the democratization of machine learning, right? You have to be careful about um, making sure that you understand the underlying math. So I had been working in the math of quantum mechanics since 1983. So, off and on working on eigenvectors and, linear operators and all of those sorts of things. And in that December of 2017, I also started working on the quantum computation piece, the math
Mm.
behind that. And so, as Sister Roswitha used to say in seventh grade, do your homework, show all your work.
Right.
So uh, th- th- there's been a ton of that. So I don't want to gloss over the fact that you do need to spend some time with uh, the quantum mechanical theory, and I think that's why you see for a lot of the more advanced jobs, they definitely want PhDs.
Yeah.
So there's there's this trade-off, and then I think one of the best quantum computing developers I've met, you know, doesn't have a PhD. So it is approachable, but there's still work you have to put in. So I wanna kind of caveat that just a little bit. Does that make sense?
Makes total sense. And thus
Okay,
your
cool.
passion, right? And, you went and through many, many years acquired that knowledge. Now, you also run a community of other passionate people within Microsoft, and if I understand it correctly, it's close to 2,000 people across the company. Maybe tell us a little bit about that community, and what you're doing to continue to stoke that fire, that passion within Microsoft.
Yeah, sure. Well, first of all, they're called the technical and leadership communities, and there's a family of about 100 of these communities of practice, and it's a great learning and knowledge sharing opportunity within Microsoft. So it's fantastic that we have that kind of infrastructure available to help support different pieces. And so um, originally it was developed to help consultants in Microsoft Consulting Services deliver better engagements, by knowing some of these different technology areas in depth. But it's branched out now into all sorts of different technology areas and um, just areas of passion. One really vibrant community within Microsoft is called the sustainability community. So it's all about the things that the challenges Mother Earth is facing right now and how we can help her. So there's and inside of the quantum computing community, we're busily kind of exchanging information, exchanging the latest articles. Some of them are very interesting, kind of clickbait almost, and just kind of some were kind of debunking and so on and so forth. And then we also have a set of study groups. So there are study groups in Redmond, in Australia, in Germany, in the Netherlands, in India, where local groups get together and work through a quantum computing textbook together. And then each of those groups records their meetings and so on. And so we funnel all those into the community so that folks who may not live near one of those study groups and may not be able to join virtually because of time zone or whatever can continue to learn. We also have a roadmap of here are some things you can do at the 100 level, and then the 200 level, and the 300 level, and the 400 level to learn this material. And so uh, we also host monthly calls from different folks, some from the quantum team themselves, some from members in the community, about topics around quantum computing. So it gives folks an opportunity from just those who are, we call quantum curious, all the way through to our friends who graduated perhaps with a degree in quantum physics and then ended up in information technology for some reason, and now have a chance to, combine those passions back together. So that's the community in a nutshell.
Yeah, and and that's a perfect segue into essentially talking about demystifying this. And I think the first step in demystifying quantum computing is really around defining it. What it
Mhm,
is,
mhm.
and maybe even most importantly, what it's not. Right. And so,
Right.
so for you, excuse me, for you, how do you define quantum computing?
Okay. It in its simplest form, right? We have classical computing devices all over the place, like this old phone here that I refuse to give up. Um, there are millions of bits in this phone, right? I mean, the basic unit of computation in a classical computer is the bit,
Yep.
right? It's one or a zero. There we go. Inside a quantum computer, the basic unit of calculation is a qubit. Okay, and folks, I'm sure have heard of qubits. They are quantum particles that you've either trapped or produced somehow, and then you're using their quantum properties to help you do the computation. So a qubit is probabilistic, meaning that its state, just like any other quantum particle, may, when you measure it, you're actually going to find out what the actual state of that qubit is. And so a qubit will use a single quantum property as its zero or its one. So spin up or spin down for an electron, for example, would be one of the common quantum properties that folks use. And so in a qubit, there's a probability of measuring either a zero or a one based on when you measure that quantum property, what the value is. Okay. Now, it turns out that you can use, and Richard Feynman originally discovered this idea and suggested it, and then it's been built upon by a number of different folks afterwards. But the basic idea is you get these qubits and you set them in an initial state, and then you apply what they call quantum gates or quantum operators on those qubits. And what that does is it pushes the qubits into a certain state, a certain probability. And the idea is your algorithm needs to nudge these different values into the right spot. So when you measure, you get the right answer. Okay, and that's the basics of computation. And you use that there's a certain set of tricks and patterns and things that come with the fact that this is a quantum particle. And then there are a whole bunch of things from uh, experiment and things like that quantum physicists have learned that you can to apply to this discipline. So if you think about it, one of the big examples that folks talk about is breaking RSA encryption.
Right.
Okay, it comes down to um, factoring large numbers, because that's a classical computer has a very hard time doing that. So when you take two very large prime numbers and you multiply them together, that product isn't immediately calculable to figure out what that what the factors are that go inside of it. Now, it turns out that Dr. Peter Shor is a quantum computing guru now. He came up with an algorithm that uses quantum interference. So it's just like the interferometer. Do you remember like the dual slit experiment and
Oh
stuff
yeah,
like that,
yeah.
perhaps? Okay, so he basically sets up these slits on these qubits, if you will, by analogy. And using the patterns of interference, you can find a factor of this very large number. And so that's how that's kind of the secret sauce behind that algorithm. And so um, things like that are lend themselves very well to quantum computing. And so that's kind of how it works.
Makes sense. And to kind of distill this down in my own words, Delbert, let me know how far off the reservation I am here. But what I think I heard you say was one key construct of quantum computing that's different than traditional or classical computing is the replacement of the bit with a qubit, right? So instead of a one
Right.
or a zero, now you've got something that can represent more than one or zero, but many, many states. Um, the second that I heard was centered around approaches and algorithms to manipulate those qubits, which we don't necessarily have a whole lot in the one or zero because of the simplicity of it. But really kind of that, that nudging that you had mentioned of those qubits to get the result that you want. And so there's many different algorithmic approaches to that. And then the third, which I think you touched on slightly, was more around the infrastructure side of the house. So there are a set of approaches that are very, very different with quantum computing than with traditional classical computing, namely being, you have to have, extremely low temperatures, virtually, well, no interference whatsoever, in a very, very controlled environment versus, we got our handy demo devices here at the ready, unlike,
Mhm.
these devices here, I don't have to worry about, recreating space like environments for it to do its job. Did I get that right?
Yeah, I think and they're depending on the environment, you can also have some qubits work at room temperature. Just kind of a little tidbit there, but I think the other piece that we want to keep in mind is a crucial difference between qubits and classical bits. And that is if I have n classical bits, I'm sorry, n qubits.
Mm-hmm.
To hold the same information, I need 2 to the n classical bits. Okay, so if you think about that exponential growth, so if I've got 4 qubits, I need 2 to the fourth or 16 classical bits. But if I go from 4 qubits to 5 qubits, instead of 16 classical bits, I need 32 and 64 and 128, and it goes up from there. So when you have something around 250 qubits, all right, that's going to be more information than you can store in enough classical bits that would equal the number of particles in the known universe.
Wow.
Okay, so that's the attraction of quantum computing. I mean, if we can work around all of these, crazy, kind of constituent parts to get there, the computational capability is just mind blowing. And so that's why there's so many companies and so many academic institutions working towards trying different approaches to have a qubit that can be stable and that won't decohere, right? As we say. In other words, if your quantum particle, that's your qubit, gets touched by a cosmic ray, that essentially measures it. Once you measure the qubit, it's in that state, right? You're stuck in that state, and you kind of have to start over. And so that's where the notions around error correction and having many physical qubits in order to make a logical qubit, and those sorts of considerations come into play. And that's why a number of the solutions require what they call a dilution refrigerator, or they need to be able to cool the environment that the qubits are in to almost absolute zero, to make sure that there's no interference from outside to disturb the qubit. Because I think, again, it was Einstein who said something like, do you mean to tell me that if a mouse looks sideways at my quantum particle, it's being measured, right? And so, and there are all sorts of different really interesting paradoxical experiments you can do based on how this measurement stuff works. And so, yes, you have to be very careful that your qubits, that you don't accidentally measure your qubits.
Right, right. Now, speaking of paradoxical situations and, pulling from cheesy 80s references of, Doc Brown from Back to the Future, we hear lots of kind of wild theories around what quantum computing can do, or essentially, statements of what can be done. One of the latest was around time travel using quantum, which ultimately it was a play on words, really not the way we think about time travel. So, given some of these things, I think what's just as important as what it is, it would be also good to hear what isn't quantum computing.
Right, right. I think quantum computing isn't something you can use on a lot of data, okay? Because it's difficult to get to get data into this quantum computer, or quantum system. You're not going to be able to learn an algorithm over terabytes of data right now. Those sorts of things. It's quantum computing just isn't suited for. Um, I think the other kind of elements of hype and kind of clickbait kind of things that happen um, are um, just kind of exaggerations of things that there's kind of a kernel of truth behind,
Mhm.
but someone's kind of gotten a hold of and twisted just a little bit to get more clicks, or more eyes on their articles. And so you have to be a little bit careful of that.
Yeah, and I know when I was at Gartner, there was a lot of that and a lot of false claims on, who's doing quantum and who isn't. And there, are definitely claims out in the press where, they say, well, we're doing quantum right now. Well, yes, but you're doing quantum simulation on classical computing hardware. And so, typically, that's usually referred to as quantum annealing. And you got all these different kind of flavors of quantum computing. I guess in your mind, do you see the same thing? And, what are the different types of things that you see in the wild?
Yeah, no, that's a great question. I think, first of all, one place that you can get started with quantum computing right now is what we call quantum inspired optimization. At least at Microsoft, and there are other vendors, other folks who offer solvers that run in, like FPGA, field programmable gate array configurations in the various commercial public clouds right now. And those solvers can work better than traditional solvers because they tend not to get stuck in local minima. So if your cost function is very gnarly, has a lot of uh, little valleys and things in it, and you're trying to find the lowest cost in there, a quantum inspired technique can help you not get stuck in what the some of the traditional solvers might get stuck in. And so that whole quantum inspired space is something you can do right now. Microsoft in collaboration with Case Western Reserve right there in Cleveland um, has developed a quantum inspired algorithm that can help with MRI signals. And the key to that is you can either get a vast, like a 2 or 3 times improvement in the accuracy of the MRI if you're willing to sit in the tube for as long as the normal MRI takes. But when you have children, especially child cancer patients, unfortunately, they they they're squirming around in that tube, and you either have to sedate them or you can use this technique and they don't have to be in the tube as long and you'll still get an accurate reading. And so, I mean, some of those kind of ideas are just fantastic for what you can do with the technology right now. The other thing that's interesting is those quantum inspired algorithms are guaranteed proof, we proved it, a quadratic quantum speed up when you actually run that on quantum hardware. So it's a little bit of a future proof, or a little bit of the ideal, if you remember the ideal behind some languages like Java and C#, right? Write them once and then run them anywhere that the JVM or .NET runs. So those things are in active development right now. And then in Azure, there is a quantum inspired optimization service that's in private preview, and it will roll into public preview relatively soon. So those things are coming, and you can do them right now. And then when it comes to actual quantum hardware, there's a company right now called Chicago Quantum that's using D-Wave annealing machines, and we'll talk about those in a second. But they're using it for valuation of stock portfolios. So certain areas where you can realize a very good material gain in exchange for the investment. You see people using quantum actual quantum hardware now, and then the D-Wave and that family of quantum computers is a quantum annealing system. They have qubits, and they're but they're more of an analog kind of computer. They have the annealing or the optimization algorithm built into the hardware. So it's kind of a purpose-built system, and the way that you solve problems is you would adopt them into this annealing framework so that the D-Wave can solve the problem for you. So it's a little bit different. Whereas other companies making what they call gate-based quantum computers, like Honeywell or IonQ or Microsoft, IBM, Google. Those quantum computers are all based on having qubits and these gates that we talked about, these quantum operations. And so those are more general purpose quantum computers.
Right.
And another term folks will hear is NISQ, which is near term intermediate, no, I sorry, noisy intermediate stage qubits. And those are qubits that are more fragile and less stable, but you use algorithms that can either get you approximations very quickly, or you use a lot of qubits and error correction to kind of help compensate for that. So there's a new paper out about saying that this new algorithm was developed that should be able to break RSA encryption as it exists now. I mean, state of the art RSA encryption with 1,000,000 noisy qubits. So when we get to the point where we've got 1,000,000 of these NISQ qubits, that could happen. And so projections right now are that could happen within the next 10 years. So folks who have information that they want to keep protected for 10 years and need to start looking at post-quantum options. And there are those being developed by, like, the National Institute of Standards and Technology is evaluating a series of algorithms. Microsoft has a couple that are progressing through those certification stages. So some of those considerations are definitely upon us.
So, you bring up a lot of really, really great points. And to kind of zero in on a couple of those, you'd mentioned the general anxiety in the marketplace around quantum, around saying, hey, all my encryption everywhere is potentially vulnerable. How realistic do you think by the time general purpose quantum computing is available, do you think we're going to have, or even if we will have that sort of scenario when we're already creating quantum proof algorithms? What are your thoughts on that?
Yeah, no, I think that we're at least in this case, I think we're going to have another kind of Y2K over this, meaning that there was enough uh, hype early on, enough anxiety and concern early on about airplanes falling out of the sky, when in year 2000, that everybody got their stuff together and found all of those 2-digit years and patched them.
Right.
So um, I think the encryption, the areas of our industry that use encryption and support it and develop it and stuff, I think are making great progress, and I think we're going to be in good shape. So I think that's something that we don't have to worry about, and I think just um, different companies in different situations should evaluate those things and evaluate the kind of I guess the shelf life of some of the information they exchange over encrypted channels over the public internet,
Right.
and start to switch over.
Yeah, I don't want to go back, and for those that remember that that time period, but I do not want to go back to the world of going through COBOL copybooks and lines of Fortran code to find these little monotonous bad ways of coding dates. I sure hope we don't have to go back to anything like that. Um,
Yeah, exactly.
but you've also, as we've been talking about these, the time horizon when this could be upon us. You know, I know this could be just a wild guess on your part, and there's lots of variables at play. But when you think about general purpose quantum computing, are you thinking that this is a couple years away? Are you thinking this is 5 to 10 years away? Do you think this is 30 years away? What kind of horizon do you look at this being available from a general purpose
Yeah,
perspective?
yeah.
Did I just put you on the
Um,
spot?
well, I want to be super careful because um, I definitely don't want to put any more pressure on my colleagues,
Right.
right, that are working on the topological qubit for Microsoft, right? So the first thing we have to keep in mind here is that this kind of quantum computation is it's science. We're still developing it. I mean, uh, Charlie Marcus, one of the he's an experimental physicist and one of the leaders in Microsoft quantum. Says that 150 years of the most ridiculously accurate scientific theory in human history proves that we will have a quantum computer. And I definitely agree with him on that. um, and the trick is when and how, right? And so my I am really, from, like, especially from a Microsoft perspective, giving dates on when this stuff will be available, or when we think it'll be available, is way above my pay grade. So the thing, though, is I'm encouraged, and folks can go and read the uh, public peer-reviewed research that Microsoft has done around topological quantum computing, and you can read through there, and I see a whole bunch of really encouraging developments. And then if you listen to the folks at IonQ, right, they next quarter, so quarter one 2021, IonQ is talking about having a 32-bit quantum computer available in Azure that's 99.9% stable. So
Wow.
that will give them a quantum volume of about 4 million. And right now, you know the the quantum volume that other folks have in their quantum computers right now is in the thousands or hundreds. So um, the other thing that the CEO of IonQ says, and he's probably looking for more funding too, right? But
Right.
he says that um, they can feasibly double the number of qubits that they support every 18 months for the next few years at least. So going from 32 to 64 to 128 to 256, somewhere around in there, right? You get to that that magic 250, 260 number, where you have a computer that's more powerful than anything we could conceivably build, as a classical computer.
Hmm.
And so those things are, just a few years away. So I'm encouraged by all of that. And I think there is plenty for folks to get busy on now.
Right.
So and I think one other uh, announcement that Microsoft has recently made is around this quantum intermediate representation, or QIR. It's basically, to use an analogy, quantum bytecode.
Hmm.
So, so any and any of the quantum computing hardware that's running in Azure right now will support QIR eventually. And so on one side, our compiler makers and quantum language makers and everything have a format they can target that will run on all sorts of quantum hardware. And then on the other side, QIR gives you the opportunity, and they just announced this at the supercomputing conference that's going on literally right now, is that QIR will let you run supercomputers side by side with quantum computers.
Oh, wow.
And so we have CPUs, right? And we have GPUs, the
Hmm.
graphics processing units for a lot of, math operations. Now we can have QPUs, quantum processing units, that these supercomputers can call a quantum subroutine to get something done that quantum is really good at, and then get the answer back. And so those kind of hybrid systems are are just around the corner too. So I think there's a lot that people can jump into right now, and of course I encourage them to do it.
Right. And I want to go back to there's a few things that you had brought up that I think pull together a common thread. And that common thread is there are many different ways of achieving quantum computing. Many different vendors. You'd mentioned D-Wave, you'd mentioned IBM, and others. They each have their own way of approaching this. And you had mentioned Microsoft's way, which is topological, but others don't necessarily follow that. And I guess trying to stay away from a marketing type of pitch, but more from the perspective of these are your views and doesn't represent your employer statement, which I was
Yeah,
waiting for you to
exactly.
say, but you didn't. So I'll just throw that
I
out there
should
into the
have. I'm
universe.
sorry. Yes, I should have said that.
So
Yeah.
we threw it out there. It's out there now. But uh, so everyone's got these different approaches, and it's a space race to get to this end state, which is we got to land on Mars or we got to get to general purpose quantum computing. And I guess for you as someone that's deep into this space, what are the pros and cons of some of these approaches? What are some of the pitfalls of some of these approaches? It'd be good to kind of get that landscape of all these different approaches and why one is better versus worse, or what are the trade-offs that you're going to make, because obviously these big companies like Microsoft, we've got tons of really smart people. There's a reason why they're doing it that way. So it'd be good from your perspective to understand what are these different approaches that these vendors are using and why are they using those and what are some of the trade-offs.
Yeah. I think first of all we could take a step back, and I can keep my Microsoft hat on, and I can do a little shameless pitch for cloud-based quantum computing, right? Is that in Azure there are three different quantum hardware vendors right now, soon to be a fourth, and you can try your algorithm on all of them. And so in some ways a space race, just like our moonshot, right, gave us integrated circuits, gave us MRIs, gave us all kinds of these great benefits that whether we actually made it to the moon or not, I think we're much better off as a human civilization. So having all of these different kinds of hardware accessible to you in the cloud is a win for everybody. So that's first. Now I can take my Microsoft hat off and just kind of talk about some of the other things.
Our shareholders
What
appreciate you doing that.
I'm a shareholder too, for
Oh,
heaven's
no.
sake. So anyway, yeah, so you have to kind of put that out there too, probably as part of the disclaimer. Um, so with the ion trap quantum computer, or trapped ion quantum computers, some of those can run at room temperature, so they don't take as much energy to operate. So that's a good thing. And they use an ion, right, a charged particle trapped in a magnetic field to make their qubits. And the pros of that are you don't necessarily need a dilution refrigerator, and the like a company like Honeywell, who's been making control systems for 100 years, now takes all of that knowledge and uses it to control qubits. And so there's a really kind of neat idea here that you play to your strengths, right? So that particular the trapped ion computers have those advantages. The trick is when you go to entangle those qubits, okay, it, the trapped ion computers work a lot better if the qubits are separated. So then you kind of have to have a little like junction to allow them to be entangled through. And there's 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 a lot behind that, but basically it it makes it harder to scale, I think. And I know that the scientists at Honeywell and the scientists at IonQ are, looking at ways to make those things work better. But that's kind of the pro and con there. One of the things about the topological quantum bits that Microsoft has, um, personally, it's just really attractive to me because I was really interested in knot and braid theory, even in college, in math in college. So uh, this is basically a similar sort of thing. You take qubits, and in order to pass them through a gate, you just change their position.
Right.
So it's these particles, some of them are what they call non-abelian, meaning that they're not commutative, meaning that if you change the order of them, it makes a difference. So topological quantum bits are harder to decohere. They're more stable. The theory tells us that they could be 3 orders of magnitude more stable than some of the available qubits right now. So that means that those qubits could live for seconds instead of thousandths of a second, which is a significant difference.
And I think this is an important point for people to understand as well, is the error rate is a vital component of all this. And maybe if I'm understanding you correctly, is one of the core reasons for going down this path is the error rates are much, much lower. Thus, you can actually get some computing out of this for longer than a, 1/10th or 1/10,000th of a second, like you mentioned.
Right, exactly. And it means that you need fewer physical qubits to make a really stable, error-corrected logical qubit. So that's the other thing, I think, is as we look at these different vendors, or if folks are kind of scratching their heads about what which of these claims are real and not, you can look at how many physical qubits do they need to actually make a logical qubit, right? And how does that error correction work? And so I think that's, yeah, you're absolutely right there. The topological qubit is intended to be um, much more stable, and um, it's it's a as you move to scale topological qubits, then I think you've got um, you have a different set of problems than folks like IBM and Google and let's see, others are those folks are implementing their qubits in silicon, and in the topological qubit, it's a nanowire. It's actually a wire you grow in a vacuum, a molecule at a time. So it's only a molecule wide wire that you use for topological, or at least Microsoft's topological qubit.
Right.
So the uh, the silicon based qubits are more susceptible to noise and less stable, but the idea is that since we already know how to mass produce silicon, they may be able to get to scale faster because they can produce a lot of these silicon based qubit chips, and then use error correction, to take care of it. And Microsoft's secret weapon in that area is a not so secret weapon. His name is Doug Carmian. He's the father of the Pentium processor, and he has come to Microsoft to help with the manufacturability of topological qubits. So I think that's just a nice piece of public information, right? Um, that gives you a sense for the confidence that Microsoft as a company has, that they're engaging a bunch of different folks. And if you go look at Microsoft's careers website and see where they're hiring folks.
Right.
Oh, gee, they're hiring folks in areas of mass producing these things. Okay, so uh, there's it's kind of these different pros and cons, and I think the best thing is that each of these companies is bringing their own unique sauce, right?
Mm-hmm.
Whether it's IBM or it's Google or it's D-Wave or it's IonQ or it's Honeywell, they're each bringing a certain expertise and a certain perspective. And so I think we can end up with quite a number of really stable systems over time. So that's a very positive thing.
Yeah. No, I agree. And, I've often referred to whenever I've been asked about some of these other approaches. I guess maybe I'm not as friendly about it, but I oftentimes have referred to it as the shotgun approach, which is, throw a bunch out there. They're not very stable, but we'll try to fix it on the back end as best as possible. And, with the topological approach, it's more of kind of a pure architectural purist type of view is let's do it right the first time. Let's not worry about kind of
Mhm.
fixing it later downstream. But I want to shift from kind of the science and what is quantum to what a lot of people are probably thinking, which is, well, this sounds really cool. Uh, we should probably get on top of this. But oftentimes it's a question of where do we apply this in our business? And I'm sure a lot of folks listening are listening to my former colleagues at Gartner and IDC and in the news, et cetera, where they hear statements, like uh, the in by 2025, the the compound growth rate of quantum computing solutions is going to be over 50%, or when quantum computing is generally available, it'll be a $10 billion market. Those are big numbers, but as we've talked about, quantum isn't for everything. It may be for everyone, but it may not be for every sort of workload that you have a problem to solve for. So, I guess in your mind, what are some of the ideal business applications for quantum computing?
Okay. Yeah, I mean, probably the simplest way to think about it is when you're doing computing, right? You have inputs, you have processing, and you have outputs, right? So for quantum computing, you like to have small inputs and small outputs, but very, very, very complex processing. So factoring large numbers is a simple example, right? You're given a number, and then there's a ton of computation behind how you factor it. Another set of great examples, and ones that are really topical for right now, are around simulating chemical processes, right? Nature is quantum, right? And so quantum computers are great at simulating processes that happen in nature. So carbon fixation is one that is a great application. In other words, pulling carbon out of the atmosphere. How do we develop catalysts that can take carbon and turn it into something that'll drop out of the atmosphere, and we can attack the carbon in the atmosphere right now. So there's that application. Another application that is, I think, very near term, is nitrogen fixation. So using a lot less energy to produce fertilizer to help feed everybody, so that's another one. It takes something like 6% of the world's natural gas to produce fertilizer, just
Wow.
because the way we produce fertilizer as humans is very high temperature, very high pressure, takes a lot of energy. Well, the darn soybeans, you plant them, and they pump nitrogen back into the soil. Well, they're not using natural gas. What are they doing?
Right.
Well, comes to figuring that out, you need a quantum computer. So folks who are doing things in material science, superconductors are another one. Um, but one that applies to just about everybody is optimization, right? If you want to make your supply chain better, you want to make your manufacturing floor better, you want to make your distribution network better, you want to make your workflow in your corporate office better. All of those kind of optimization things, quantum is very good at, and you can use the quantum inspired stuff now, and you can develop your quantum algorithms around optimization. And so that's a great use case that just about everybody has.
Right. Yeah, and if I hear you correctly, what you're saying is if you've got, a controlled set of data, not a huge amount of data, we're talking about, a good, controlled set of data, and you know the problem that you're trying to solve, and it's complex, it's multidimensional, you want to run modeling simulations, things along those lines, quantum computing could be a really good solution for that versus classical computing.
Correct. And I think the other thing is there are a number of companies out there who have been bitten by, like, the data science thing. They
Hmm.
they got a little bit behind in their data science practice, and now they're scrambling to catch up because their competitors are using machine learning and beating them in certain areas or whatever. And so the uh, the counter to that is to take employees you have now who are passionate about this subject and just give them an environment where they can start learning and start preparing for this. And so as a company, it's a reasonable investment in your future.
Right.
So that's another kind of way to think about it. So you want to grow that capability, and
You know,
then
I
yeah,
like what you're saying because it validates a point that I made a long, long time ago. Probably maybe 10 years ago when the big data movement was really starting to build up some steam. What I would tell people, and people looked at me like I had, five heads, was, you know, big data without big insights is a big problem. And what that means is, okay, so I've got a lot of data, but if I can't do anything with it, I might as well not have the data.
mhm.
And how much of that data is actually valuable. And by collecting all this data and putting it into a data lake or what have you, it actually might complicate the issue even more. And so, what we're learning from some of these emerging technologies, well, a lot of these emerging technologies like artificial intelligence, it's all about having really good quality data that you train, etc. Likewise with quantum, likewise with blockchain, and the list goes on and on and on. So it kind of comes back to those information architects. I'm sure that they're super excited right now. They're like, see, I told you guys.
I was right all along.
Right, right.
Yes. And the thing is those information architects are kind of curmudgeony, aren't they? Usually, so yeah, they're waiting to poke us a little bit on this one.
Right. Now, so that's super interesting on the patterns, where it makes a whole lot of sense. And I guess in a similar theme as we talked about what isn't quantum computing, applying that to what are not good scenarios for quantum computing. Are there specific things that aren't good for quantum computing? Like for example, I've told people, you'll never see this as a quantum computer, as an example, or it doesn't really make much sense. At least in my mind, it doesn't. What do you think are really, really bad quantum computing applications?
Yeah, I think big data, probably stuff you're trying to operate over big data, at least in the near term. Um, Quantum machine learning is a really interesting one. I think over time that's going to be a very good use case, but it might not be a good use case right out of the gate.
Right, right. No, it makes sense. And again, it continues that theme, with a whole lot of poorly organized data isn't really a great application of this. So I could imagine things like when we'd mentioned supply chain, things like digital twins, and converting this data into tokens and running simulations and models around that would be a super useful use of quantum computing.
Hmm. Yeah, I think so.
So as we start to wind down a bit, Delbert, it'd be good to understand, as people are consuming all this great knowledge from you because you've given us a ton to chew on. What would be the one takeaway that you would like people to impart from this conversation, uh, about what you're talking about? And
Yeah,
I'll be generous. You can give them a couple, but less is more here.
yeah.
What would be some of the things you really want to leave people with?
I think the first one is start now. Don't don't wait for um, the full scale quantum computers to come out, because by then it'll be too late. And I think the other thing is you can start now simply by you know developing internal staff who are passionate about this subject, and some targeted hiring. So I think that's really the first thing, and try and experiment and perhaps fail and learn a little bit here along the way.
I love it. And obviously, Microsoft is making huge investments in the developer tooling to make that a reality, like you'd mentioned. So, listen, Delbert, this has been phenomenal. I really appreciate you taking the time to walk us through this. If people want to get a hold of you, what's the best way for them to get a hold of you?
Probably just through LinkedIn, I think. And so just Delbert Murphy in LinkedIn and probably say Delbert Murphy Quantum, and that'll get you right to me.
Yeah, I know whenever I tell people go search for Mike Walker on LinkedIn, and yeah, good luck. I think I'm on page 55 or whatever it may be. But again, Delbert, super fascinating conversation, and looking forward to having you back again sometime to continue the conversation.
Yeah, and to give an update, hopefully we'll have some more breakthroughs that we can talk about.
Yeah, I'm sure we will. All right, Delbert, thank you. See you next time.
Terrific. All right, you're welcome.
All right, guys, that's a wrap. I hope you enjoyed this episode and you got something from this. Remember that all the resources that we talked about today will be available on vnextpod.com. That's vnextpod.com. So, for all the links and show notes that we talked about on today's episode, you can find those there. But also remember to like and subscribe to our channel. It helps us know what interest is out there for this type of content, but also you'll be able to be alerted once there are new episodes. So definitely like, subscribe, rate, all that good stuff. So until next time, bye now.